This slide set covers motion and energy, and it deals with energy relationships and transfer. This is for Physical Science GNSC 1204 at MSU Texas. First topic I want to talk about is pressure. So far in this class we've spent a lot of time talking about forces. Recall that forces are what Newton used to describe motion, and the second law equates these to masses that are being accelerated, provided we use the same units. But what we can measure in the real world is pressures, and pressures are just forces applied over an area. P equals FA. Remember that area is distance times distance. That's kind of important. So pressure is in the units newtons per meter squared, or if you want to break that out further, that's kilograms per meters per second squared, or in the imperial units, pounds per inches squared, or PSI as you might know it. Consider the figure on the right. A package and delivery person is 735 newtons in terms of force applied to the surface of the planet. The force is actually applied over the footprint of the individual. Estimating the area, that's about 0.06 meters squared. That would make the pressure 735 newtons over 0.06 meters squared. Solving, that's 1.225 times 10 to the fourth newtons per meter squared. By the way, a newton per meter squared is a unit known as a Pascal. More on that later. This slide should look familiar. We've talked about this previously, but let's revisit in terms of pressure. Remember, we use this to talk about work and the difference between the balloons that are uninflated on the left and those on the right are that work has been done to inflate them. Let's recall that the equation for work that we're using is a force through a distance, that is F times d. Well, if pressure is force over area, we can rearrange that so that a force is pressure times area. Popping that into the work equals F times d equation, you get work is equal to pressure times area times d, or distance. And area times distance is a volume. So a way to think about work is pressure times volume. Another important idea we should reconsider is our reference point in terms of distance. Recall that in many of our problems we've been using 0 as the ground level and talking about the distances as change in elevation above that. This makes sense if you're talking about a falling flower pot that's going to hit a sidewalk. The ground is the place where we will decelerate, and our positive distance above the ground, elevation, or delta H, is the important parameter. But what if your mass has the potential to fall even further? Well, realize that the ground level was just an arbitrary point. We could have chosen the center of the Earth. Let's consider, though, that if we want to keep the ground as our level, that we might have to define things in negative space. Recall that potential energy described the amount of work that we did to get a mass to a certain elevation. The mass, m, times the acceleration due to gravity, g, times the change in height, or h, or delta h, will give us the change in potential energy. If we think of it as just changes, that actually helps us out. Consider a weight on a table that is now above a hole going down to the basement. We could still define our 0 level as ground level, but we need to realize that we could be operating in negative space. Sometimes this is useful to see how potential energy changes relative to a fixed position. I want to take a minute and explore the relationships between potential energy and kinetic energy, or more specifically, work and kinetic energy. We used two separate equations previously to talk about the phenomenon of work and potential energy to that of kinetic energy. But there is a connection. It's not an easy one to see. And don't worry if you follow every step on this slide. I just don't want to sweep anything under the rug. So let's take a quick look at what we're doing here. Recall that work is equal to force times the distance, which is also our equation for potential energy. And we talked about kinetic energy as being the energy of motion, so velocity was involved through this equation, 1/2 mass times the velocity squared. Let's break it down. Acceleration is equal to the velocity change over time. We defined that pretty early on in this class. And that means a v final minus a v initial over a change in time. Solving for v final, as we've done before, we get v initial plus at is going to be our equation to represent v final. But we can plug in Newton's second law, solved for acceleration, so our equation becomes v final is equal to v initial plus force over mass times the change in time. Let's move to velocity at this point. Recall our initial velocity equation is velocity is equal to distance over time. That means the average velocity should be equal to the change in distance over time as well. And if we solve for distance, we get velocity average times time. And we got the average velocity by multiplying 1/2 times Vf plus Vi times the change in time. Next step is we can eliminate the change in time. Newton's second law says that force is equal to a mass times an acceleration, and we know that an acceleration is the change in velocity over time. Therefore, Newton's second law could also be written as force is equal to mass times a change in velocity over a change in time. Change in time can be solved for mass times a change in velocity over the force, and that means we can multiply it out by our average velocity, m times fv minus m times vi over force. That means our change in distance is equal to the average velocity times the change in time, and written out it looks something like this. And of course we can divide it by the force, meaning that when we resolve all this down, our expression is 1/2 mass times the velocity final squared plus 1/2 mass times the velocity initial squared over f. If you set Vi equal to 0 meters per second, in other words, if it's stationary to begin with, then the amount of work that's involved is equal to force times the change in distance, or 1/2 mass times the final velocity squared. In other words, we can get work to be in terms of kinetic energy. And we sort of knew that because kinetic energy can be completely transferred in potential energy, and potential energy can be completely transferred into kinetic energy. They have to be equal. Again, this is not required, but if you can follow this connection, you've made an important step in understanding the relationships between the two forms of energy, that is potential energy, which we got from work, and kinetic energy. Now back to material you're responsible for. We've gotten the idea from looking at pendulums that potential energy can be changed entirely into kinetic energy, and vice versa. That means any form of energy as we want to describe it can be exchanged. Let's look at Olympic sport as an example. You might have gathered from the video of Veritasium interviewing Rod Cross that sports and physics go together. So what exactly is happening in some of these sports? Archery, for example, is drawing a string back against its inertia. When the string is let go, we get an increase in kinetic energy depending on how far back the bow was extended. In weightlifting, of course, we're working against the fundamental force of gravity, and that means an increase in potential energy, much like our flower pot and the weight on the table. However, we can think about other fundamental forces as well, magnetism and electrostatic forces. Those will come up later in the semester. Friction is complicated because you're seeing a transfer in both potential energy and kinetic energy. An Olympic sport that uses this is the sport of curling, where granite stones are glided across an ice surface, and teammates use friction against the ice to guide its path. Shape is important as well, and we'll see this in springs and elastic media in general. We certainly see this in springboard driving, where an increase in potential energy allows for a higher arc to the dive. One last point about friction. What we're seeing is actually an increase in heat, which is both potential energy and kinetic energy. We'll consider heat as a property on its own in later slides. And in fact, what we really want to do is be able to talk about energy in some kind of competent manner. And that may mean breaking it down into different sub-boxes. Just keep in mind that energy is energy, no matter what label we give it. Kinetic, potential, or some of these other labels that are commonly applied, like mechanical energy. I think mechanical energy is perhaps the most visible and intuitive form, and of course includes the motions of the human body, but we certainly see it in the extensions that we've made through technology. Consider the kinetic energy of a moving object, like a car on a racetrack, or the kinetic and potential energy of a flywheel. Flywheels are important to some engines because if you're asking an engine to stop and start an object, you may want to store the energy and keep the engine going. Flywheels can do that. A spring has potential energy when it's compressed or extended. More on that later. Compressed gas, of course, has an energy as well. And water behind a retainer, like a dam, has the potential energy of gravity. That water wants to flow downhill, but the dam is keeping it at bay and raising its elevation. Two other forms of energy we'll spend considerable time with are chemical and radiant energy. Chemical energy is that stored in chemical bonds, and there are numerous examples of this. But perhaps the easiest to see is when we combust something like petroleum, coal, or wood, or the metabolism we have in our bodies using food for energy. And certainly explosives are an example of this. Consider the picture of the campfire on the right. Campfire has wood materials which are being oxidized to release energy. There's also some chemical byproducts. We're breaking down the bonds in the molecules that make up the wood to transfer it into carbon dioxide and water, and the process releases energy. Radiant energy is that energy that travels through space, and in fact works best when nothing is in the way. Much more on that later. The fire is an example of it, but perhaps a cleaner example is a hot burner. When you have a stove burner on red hot, that means that you're actually seeing emitted light. But even on medium or low, you can feel the heat coming off the burner. And that's infrared radiation. What you're experiencing is a small part of a continuum we call the electromagnetic spectrum. Visible light, including red, is a function of how much energy is being transferred. Infrared, the heat you can feel, is just below it. But there are other forms of energy on the spectra, including radio waves, television, microwaves, yes, those used in the ovens, ultraviolet, the stuff that you get from a sunburn, X-rays, and gamma rays. We'll talk more about how we categorize these by wavelength, frequency, and magnitude in later slide sets.